So that is a strong acid. What is that?
It's a weak base.
Why is it a weak base?
Because it'll make carbonate. Some of it will make carbonate.
Really?
No. No, that's
I
part
just
of
thought
the
it sounded confident.
We'll come back to this one. Okay. What's that? What do you think that is?
Did you say weak acid? Weak base? How many cents an acid?
Well, she was right.
Ah, see, there you go, I just helped you out. You're welcome.
We'll come back to this one too. We'll see why that one's a weak base, that one's a weak acid. And what is NH3?
A weak base.
It's a weak base. You put it into water, and it's going to make OH minuses. It's going to react with water to become NH4 plus. It's going to steal a hydrogen from water to become NH4 plus, leaving behind OH minus. So you're going to make OH minus with that. It is a base, but only some of them are going to react with the water to make it. So it's a weak base. Just looking at that picture and that picture, which one is HF and which one is HCl?
A is HCl,
Why is A HCl?
because they're, this is a strong acid, so it makes the third green one, so the acid is bigger maybe? Stronger? Okay. It does make sense that way.
Strong electrolytes.
Why?
I was just trying to.
What's different between, other than the green versus the yellow and the size of the green versus the size of the yellow? What's different between them?
Hydrogen bonding.
I guess there is hydrogen bonding in the HF one, but that's not relevant.
That's the wrong answer.
Or it could be the bigger one?
Just looking at them, what's different between the green ones and the yellow ones, other than the size and the color?
There's more green ones?
No,
Not a circular.
I'm pretty sure they're all circular.
Okay.
Spherical.
What's different between them? I mean, you're,
So they have
Bonds?
one of the white ones.
yes, yes.
Are they bonds?
The green ones don't have any white hydrogens on them. The fluorines, some of them have the white on them. Over here we have a bunch of these. These are the hydronium ions. The white hydrogens came off the chlorine onto a water to make hydronium. Over here, this is HF. What do you remember about HF, about fluorine and electronegativity?
It's the most.
It's the most electronegative. And what is electronegativity?
Most electrons, this is a lot of electrons, or no?
Electrical flow.
What about electrical flow? You're on the right track.
It's the kilowatts?
No.
It's the wattage. It's the wattage.
It doesn't conduct very well, or?
Electronegativity is how strong the pull is on electrons. And so what's going on here, remember we said HCl and HI were strong acids. HF actually sometimes will act as a weak acid because that fluorine is so electronegative it doesn't want to let the hydrogen go. So that's not an example. Exception. That's where HF is an exception. So HF is a weak acid. So you can tell based on the picture which one is HCl, which one's HF. This one completely broke apart, and this one only some of them broke apart. Only one of them broke apart.
Does hydrogen bonding have anything to do with it?
Yeah. A. Strong acid, strong base, weak acid, weak base.
Weak base.
Why?
Blue, not green like the rest of them. Because it's a base color, so it's blue.
Bases are blue.
Basic blue.
There's
We
some
got
with
it.
two,
On the pH scale, the color.
there's some with 2, some with 3, and there's hydroxides floating around, which means it's still some.
Exactly. So these, well, I think if you're far enough away, you can't, the ones that you thought had 2 actually have 3, and the ones you thought had 3 had 4. But that one, and that one, and that one all have 3 hydrogens on it. That one, and that one have 4. These are waters that lost the hydrogen. So 2 of these blue ones stole the hydrogen from waters. What weak base do you think that is? What has an atom and 3 hydrogens on it? Ammonia. So ammonia will make NH4 plus and OH minus. And these are the 2 that we just looked at. Strong acid, strong base, weak acid, weak base. It's a weak acid because only some of them broke apart to make hydronium. That's a strong acid because they all broke apart to make hydronium. Some of our acids have more than one hydrogen on them. The HCl has 1, HI has 1, HF has 1, acetic acid has 1. Some of them have multiple. We call these polyprotic acids. Poly for multiple, protic like proton or H+, so there's multiple protons on them. And so if you have multiple protons, multiple hydrogens on your acids, those acids can donate more than 1 proton. But they come off one at a time. So if we take sulfuric acid, H2SO4, and you put it in water, one of those hydrogens is going to come off and join onto the water to make H3O+. Then the second one will grab onto a different water to make H3O+. They don't go in pairs, they come back completely independent of each other. Phosphoric acid has 3, carbonic acid has 2. Here's a reaction. Which one is our acid? Which one is our base? That is saying they're reactants. So you just got 2 things over here. One of them is acting as an acid. One of them is acting as a base. Which one is which?
H2O is the acid.
Why?
This is going to give away a hydrogen.
Exactly. When you want to figure out which is the acid, look for which thing gave away a hydrogen. So here we have H2O. If you lose a hydrogen from that, you're going to get OH minus. So it took a hydrogen from here and it went on to here to make HOCl. The base is the thing that gains a hydrogen. So this gained a hydrogen going over to here. So in this situation, what's our acid? What's our base? Which thing is giving away a hydrogen?
The sulfuric acid is obviously acid.
Yes. If you know a sulfuric acid, you can probably guess that's an acid. How can you tell from up there?
A bit, yeah.
Great. You can look at it one way or the other, whichever one your mind wants to grab onto. So Zach said the fluorine is gaining a hydrogen, which makes the fluorine a base. So by default, that has to be the acid. You can also look at it the other way. I tend to find the acid first. I say, I started with that, I ended with that. This is that minus a hydrogen. And so that must have been the acid. How about here? What's their acid, what's their base? Which one is giving away a hydrogen. NH4 gives away a hydrogen to go from here to here. And in this case, the water is gaining it to go to H3O+. So NH4 plus is an acid. Where on the previous slide, I think it was the previous slide, did we make NH4 plus? How do you get NH4 plus? NH3. So when you put a base in water, you make an acid. That's conjugate acid and base pairs. When you add an acid to water, you actually end up making a base. When you add a base, you make an acid, and you get these pairs. Okay? So just looking at this, just like we did, which one of these is our acid? The HF is our acid. So that's our acid, so by default, that's our base. Those are the easy ones to pick out. The other half to doing these conjugate acid-base pair questions is to figure out on the opposite side, on the products, which is your conjugate acid, which one is your conjugate base. And the way you do that is you take your acid, you remove a hydrogen from it, you find what's left on the other side, and that is your conjugate base. And so we've now identified the three things, so by default, that is our conjugate acid. The conjugate acid is the thing that gained the hydrogen on the product side. That's the conjugate acid. Because this is actually in equilibrium. These can go backwards to that. And so if we were to flip this around, this is giving a hydrogen to the HF. So that's an acid. And that is gaining a hydrogen, so that's a base. So this goes in both directions. Find your acid, take a hydrogen off of it, find it on the right side, that's your conjugate base. And so you're probably in your homework, quizzes and things, you will definitely see this and have to label the acid, the base, the conjugate acid, and the conjugate base. I guarantee you will see that multiple places. So, like this says, and we saw, they always differ by one hydrogen. So we said some of them, the polyprotic acids like sulfuric acid, have two. What would be the conjugate base of sulfuric acid, which is H2SO4? What is the conjugate base of that? What, just SO4?
That's also negative, positive. HSO4 negative.
Yes. The conjugate pairs differ by one hydrogen. So Dominique was on the right track. He took both hydrogens off. The conjugate pairs differ by only one hydrogen. So you take one hydrogen off, now you have HSO4, but then when that hydrogen left, it is now down here, it has a positive charge. You can't magically make charges. And so if that has a positive charge, this now has a negative charge. So that is the conjugate base of sulfuric acid. And so what would be the conjugate acid of ammonia? Conjugate acid. Conjugate acid. It's NH4. You're going to add.
Right.
When you add that hydrogen, you're adding one of these.
Oh.
So it's positive, exactly. So you take that, that's our base. We add that, we get NH4 plus. The hydrogen went with 3 to the 4, and the plus came up here. So that's the conjugate acid of ammonia. So when you're asking for pairs, just change the hydrogen by 1. If it's asking for the conjugate acid, add it. If it's asking for the conjugate base, take it off. This is another example like what we did here. This is phosphoric acid. The conjugate base of phosphoric acid is H2PO4 minus. You don't get rid of all of the hydrogen. You just change one at a time. So what is the conjugate base of carbonic acid? HCO3 minus. Conjugate base of phosphoric acid? H2PO4 minus. What about that? What's the conjugate base of that? PO4 3 minus. Yes. You only got one hydrogen left. Take it off, but you still have to make your charge one more negative. So you go from -2 to -3. It's the conjugate base of that. NH3. You go from 4 to 3, and you take plus +1, subtract 1, and you come back down to 0. It's the conjugate base of water. OH minus, hydroxide.
Because the ones that aren't positive to begin with become negative because you're pulling out a positive, but if the ones that are positive to start with, you're like canceling out the positive, so it's just regular. There's no connection.
Think of it like a number line, okay? If that's 0, okay, when you take off an H plus, you go 1 to the left, okay? So if you're at 0 and you go 1 to the left, you end up at -1. If you're starting at -1, you're going to go 1 to the left, and now you're at -2. But if you're starting up here at +1, you're going to go 1 left, and now you're at 0.
Okay, it's technically positive 1, but you just have the pluses.
Yes. The ones are unfortunately always assumed. It's the conjugate acid of sulfate. Yep. Add a hydrogen, HSO4, add a +1 charge. So you go from 2 minus to 1 minus. So HSO4 minus, conjugate acid of that. H2CO3 neutral.
Oh, nothing.
Neutral. We went from -1 up 1 to 0. NH2. Hey guys. Thank you.
NH3 positive or NH3 neutral?
Yes. NH3 is a conjugate acid for NH2 minus. And so that may have made people think about what I just said. NH3, acid or base? It's base. But we just said it's the conjugate acid of NH2 minus. And so it all depends on the scenario.
This is like the reducing and oxidizing agents in bases.
So if you were to be asked, NH3 is acid or base, it's a base. But if you have this, which would very, very, very rarely even exist in real life, compared to that, it is an acid. What about that? What's the conjugate acid of that?
HCl3.
HCO2 neutral. You're just adding a hydrogen. H2PO4 minus, conjugate acid is
H3PO4.
H3PO4. That's not hard, right? So, this is starting from scratch. This is like what you would see on a quiz. You have to find the acid and base, conjugate acid, conjugate base. I like to start the acid and base on the reactant side. So what is the acid, what is the base?
H3PO4 is acid.
H3PO4 acid, so by default, that's the base. Now we've got two of our four. Now, on the right-hand side, which is our conjugate acid, which is our conjugate base?
H2CO3 is a conjugate acid. The gain so.
Yes. So this started as the base. The thing that starts as the base becomes the conjugate acid. So by default, that is our what? Conjugate base. And that came from that, which was the acid. The acid makes the conjugate base. So now we're going to start talking about pH. Okay? And pH is determined by two things. Concentration of hydronium ion, which is exactly the same as the concentration of H+. It's just this is the more technically correct way of writing it. And it's also determined by the concentration of hydroxide ions. If we have a neutral solution that's not acidic, it's not basic, the concentration of hydronium or hydrogen ions is exactly equal to the concentration of our hydroxide ions. If all of a sudden we now have more hydronium than hydroxide, it's acidic, which makes sense because when you add acids, you make that. When you add bases, you make that. So if you have more acid than base, you have an acidic solution. If it's the other way around, if you have more hydroxide, if you have more base than acid, you have a basic solution. Do you think, if you have a basic solution, are there hydronium ions there?
Yes.
So you say yes. Why?
Because I mean, the H3O, the hydronium ion.
Yeah. So if you have a basic solution, you're going to add some base. Say that number is 3. If that's 0, though, 3 is more than 0. So 3 is more than 0, it's also more than 1. So you can't necessarily do it mathematically. If you have an acidic solution, do you think there's a hydroxide present?
Is there any way to really know?
Just experimentally. And we'll. If you have a neutral solution, you wouldn't seem like you would have either. If you have a neutral solution, you just have water, and you don't add acid, you're not going to have any of that. If you don't add a base, you're not going to have any of that. So it should be 0 and 0. It would seem in an acidic solution, if you add HCl, you're going to make some of that. But you're not going to make any of that. If you add a base, you're going to make some of that. But you're not going to make any of that. So it would seem like you're not going to have OHs in acid, H3O pluses in basic solutions, or either in a neutral solution. But we do. And that's because water is weird. Of all the molecules we talked about the entire semester, water, which would seem to be the simplest one of all of them, is the weirdest. Water will all of a sudden break apart on its own. It's self-ionizing. If you have two water molecules, they will actually switch and make H3O plus and an OH minus. H plus came from this water over to that one to make hydronium and hydroxide. So if you have a glass of water, you have hydronium and hydroxide present. So if we go back, in a neutral solution, there are both present. It's just there's always one for the other. You can't make one of these without making one of those. So they always completely and equally cancel each other out. If you look at the product, so the multiplication product of the concentration of hydronium times the concentration of hydroxide in a water solution, they always, always, always equal the same number. And that number is 1 times 10 to the negative 14. I don't think that is on your cheat sheet. No, that number is not on your cheat sheet. That's something you're going to want to remember. The value of Kw is 1 times 10 to the negative 14. And so mathematically, if that is always equal to 1 times 10 to the negative 14, if we have a neutral solution, that has to be equal to that. And so mathematically, that has to be 1.0 times 10 to the negative 7th, and that has to be 1.0 times 10 to the negative 7th. Because when you multiply numbers with exponents, you add the exponents. So if that times 10 to the negative 7, and that times 10 to the negative 7, and you multiply them, negative 7 plus negative 7 is negative 14. So we're going to use this a lot. Because if you can find the concentration of that one or that one, you know the concentration of the other one. Because Kw is a constant. If they always have to equal times 10 to the negative 14. If we have an acidic solution, this is going to be high. If we make an acid, if we add HCl, we're going to make H3O+. And so if that goes up, this has to go down with it so that this number doesn't change. So in an acid solution, we do have OH minuses present, but there aren't very many of them. On the other hand, if we add something like sodium hydroxide to water, we're going to get these. This is going to go up. But when that goes up, this has to go down so that the product between them doesn't change. So, in a neutral solution, the two are equal to each other. They both are exactly 1 times 10 to the negative 7th. And so Kw is 1 times 10 to the negative 14. In an acidic solution, Kw is still 1 times 10 to the negative 14. But in this case, the hydronium ion concentration or the hydrogen ion concentration is going to be more than where it started in the neutral. And when that goes up, that one has to go down. In a basic solution, this one, the OH minus, is going to go up. And here, the H3O plus is going to go down because that went up, and this has to stay the same. So, you can tell just by looking at one of these, whether the solution is neutral, acidic, or basic. So let's just look at the H3O plus. If the concentration of H3O plus is 1.0 times 10 to the negative 7 exactly, it is neutral. If it's more than that, it's acidic. If it's less than that, it's basic. So, like I said, if we know one, we can find the other. So if Kw is H3O plus times OH minus, we can solve for OH minus, it's just Kw over H3O plus, right? And so that's a constant. And so OH minus is just a constant divided by the concentration of our acid. You can also do it the other way. If you know hydroxide, you can solve for acid. It's always Kw divided by the one that you know. So, if this is our H3O plus concentration, what has to be our OH minus concentration? 10 to the negative 9. You didn't even use a calculator. How did you do that?
14 minus 5.
Why is it 14 minus 5?
14 is like constant of 14.
Right.
And it's an exponent, so you're going to add them.
Right. So if we go back here, he knew the because when you multiply exponents, you add them. So he knew the two numbers added together have to be times 10 to the negative 14. So if that is negative 5, 10 to the negative 5, that has to be 10 to the negative 9. Is that acidic or basic? That's acidic. Even though 5 is a smaller number than 9 because it's a negative exponent, 10 to the negative 9th is a smaller number than 10 to the negative 5th. Don't get that mixed up. So this is our H3O plus. What is our OH minus? 10 to the negative 2. Acidic or basic? Basic. If this is our OH minus, what's our H3O plus? 10 to the negative 8. Yeah. Acidic or basic? Basic.
No,
Basic. You get negative 6, negative 8. What's this? 10 to the negative 2. Oh, I thought you said 6. Yes. 10 to the negative 2, acidic or basic? Acidic. So you can easily go back and forth between these, especially when you don't have a number in front of the 10 to the negative 6. We'll get into problems where it's like 3.2 times 10 to the negative 6. Then all of a sudden that math goes out the window. So here's the first example. OH minus 2 times 10 to the negative 8. He's not going to do that one in his head, I don't think. How can you do this?
Divided by 1 times 5 times 10 to the negative 14 divided by that.
I think what you have in your mind is correct, but the way you phrased it, it's upside down.
Yeah.
So the KW, the 1 times 10 to the negative 14, is going to go on top. And you're going to divide by that. So KW is H3O plus times OH minus. So we know OH minus, so we're going to solve for H3O plus. Equals KW divided by OH minus, which equals 1 times 10 to the negative 14 divided by 2 times 10 to the negative 8. And that, yes, you would calculate. And our calculator man is missing today. Yeah.
This might be a little off topic, but wouldn't glaciers be made out of more OH because they have like a higher base? Like a strong base. The glacial water is supposed to be really like basic, you know what I'm saying? Versus like.
I've never, I don't know, I'm not saying that's not true, I've just never heard that.
Okay. Well, I was just thinking because OH has less molecules that it would have a lower freezing point than H3O. So if you froze water, would it be less acidic? Like it's the core of it, not on the outside of it. Like first freezing water would be the less acidic, right?
When you freeze water, all of a sudden, you're not going to have these anymore, I don't believe. I think when they freeze, they're going to come back together.
5 times 10 to the negative 7.
5 times 10 to the negative 7. So I'm sorry, I can't give you a better answer than that, but it's not something I'm familiar with. So we have 5 times 10 to the negative 7. 5 times 10 to the negative 7 what? Don't forget units. Molar. That was molar, so we're going to get molar. When you're dealing with this, therefore with our brackets, it needs to be molar. With anything other than molarity, you're going to get the wrong answer. OH minus is that. What are we going to get? So it's going to be 1 times 10 to the negative 14 divided by 0.035 is equal to what? Just 2.9?
Well, it's 2.8571.
Right. It's not times 10 or something?
Yeah, like times 10 to the negative 13.
10 to the negative 13. Molar. And that's a definition. That's 1 times 10 to the negative 14. So our sig figs are going to come from that. So you just KW divided by the one that you know gives you the other one. So we're going to take it one step further back. These questions don't give you directly either of them. You have to figure out what one of them is based on what type of solution you have. So, first one, we have 0.10 molar HCl. Is HCl an acid or a base?
Acid.
It's an acid. And so, what concentration of H plus ions are we going to get in a 0.1 molar HCl solution?
Acid.
I'm looking for a number. What concentration?
Aren't you going to go moles to moles to figure out?
If I said I have a 1 molar, we'll go with sodium chloride, 1 molar sodium chloride solution, what concentration of sodium ion do I have? Thank you. 1 molar. So if I have a 0.10 molar HCl solution, what's my concentration of H plus? 0.1. You just take that. It's a strong acid, so it's going to completely dissociate. So the concentration of my H plus is the same as the concentration of my acid. So we have 0.10 molar H plus. In our equations here, it's not written as H plus, it's H3O plus. But that 0.1 molar H plus immediately becomes 0.1 molar H3O plus. So now we know that we can solve for that. So we have 1, I'm going to start writing shorthand with an E, negative 14 divided by 0.1 is equal to what?
1 E negative 13.
1 E negative 13. Yes. And so 0.1 is the same thing as 1 E negative 1 exponents have to add up to 14. So this one was easy because they're 1s. What if we have 0.1 molar NaOH? What do I do with that? Same thing, but the 0.10 is my OH minus concentration. So I plug it in here, the math is going to be exactly the same, but this is now my H3O plus concentration instead of my OH minus. What if I have that? Which of these two numbers do I know? I know the H3O plus. It's hydrochloric acid again. So that is my H3O plus concentration. So we have 1 E negative 14 divided by, this is 1 E negative 1, 2, 3, 4.
1 E negative 10?
So the answer is 1 E negative 10 molar. So it's very easy to go back and forth between them. And if you're just dealing with ones, you can do it in your head. If we have these, we can start talking about pH. You've heard about pH. What do you know about pH?
The scale.
You all.
The pH, if you calculate it, is the negative log of the H3O plus concentration. Make sure you have a calculator that can do logs. You do not want to be sitting here trying to do logs on paper. Okay? If anyone can do a log on paper,
You pass
you
on that.
you get a round of applause, but I can't pass them. Yes.
And we're actually going over log and doing it on paper in my math class.
Good.
So.
So, it's negative log of H3O plus. And so, what is the pH of a solution of H3O plus of 10 to the negative 1? If you have simple numbers like this, you can easily do logs in your head. Who has taken math and can tell me the negative log of 10 to the negative 1? Yes. How did you do that in your head?
What power of 10 gets 10 to the negative 1, and then, so it's negative 1, and then negative is 1.
Yes. So that is the theory of a log. So you're correct. How did you do it?
But as far as that, all logs that with log 10 with a number at the top is usually always the same number, unless in this case you take the minus off.
Right. So you're both right. The way I look at it is I say what a log does is it takes the exponent and brings it down out of the exponent's place. So if I take the negative log of 10 to the negative 1, I have negative log 10 to the negative 1. That's going to take the minus 1 and move it, where I want to put it. It's going to put it there. So now we have negative 1 log of 10. The log of 10, yes. What?
I was gonna say, so you could just divide the whole thing by negative 1 and then it's whatever's above the 10. You know, to
Yeah.
remove the first negative. You know,
Yes. So, what is the log of 10? Log of 10 is 1. So now we have negative 1 times 1. If we double negative, that becomes positive. 1 times 1 is 1. It's 1. So, in short, all we did is we took that number and made it positive. That is the negative log of that number. So what is the negative log of 10 to the negative 5th? 5. Negative log of 10 to the negative 7? 7 and 11. So that is how you find pH. You have to have the H3O plus, take the negative log of it. The calculation is going to get a little more tricky if this was 3.8 times 10 to the negative 1. Then it gets a little area. Which ones of these, based on what we know about H3O plus concentration in relation to neutral, which ones are acidic, which ones are basic, which ones are neutral?
1 is 5 or acidic, 7 is neutral, 11 is basic.
Yeah, so we said if the H3O plus is 10 to the negative 7, it's neutral. These concentrations are larger than that one. That's acidic. This one is smaller. It's basic. So if you look at the pH scale, a pH of 7 is neutral. If you have a number lower than 7, it's acidic. If you have a number larger than 7, it's basic. So here is our pH scale. Here we have the H3O plus concentrations and the corresponding pH values. Pure water is 7.0. Tap water is not pure water. It is not 7.0. So you just look at some of the things you're familiar with here. Detergent is about 10. Milk is 6.5.
Milk?
Yes, I'm from up north. It's milk. It's not milk, it's milk.
Oh my god.
Milk in the cow, man.
Who?
Moving on to beer. Beer's 4 to 4.5.
Does that depend on how much alcohol's in the beer? Or is that just
How much
depend
you
on
can
how
see.
it's brewed?
Alcohol changes. Ethanol is slightly acidic, but most of this is coming from other stuff. Lemon juice is 2, a little more than 2. Stomach acid is about 1. So this is a log scale. Have you ever heard of the Richter scale? What is the Richter scale? Earthquakes. That's how they measure earthquakes. The Richter scale is a log scale also. Have you ever heard when they say in the Richter scale, a Richter scale 6 earthquake is 10 times more strong than a Richter scale 5? You ever heard that?
Yeah.
That's how a log scale works. If this is 10 to the negative 6, and that's 10 to the negative 7, that is 10 times more concentrated than that. And so if you look at the pH scale, that's 6 and 7. So something that's a pH 1 is 10 times more concentrated than a pH 2. A pH 1 is 100 times more concentrated than a pH 3. The difference between them is how many powers of 10 they are apart. So our pH scale goes from 1 to 14. But this is the traditional scale. It is possible to go off this scale. If you get a negative pH number on a quiz or something, trust it. Assuming you know you did the work correctly, it is right. If you get a pH of 15 and you know you did your work right, trust it. It's just that in real life, most things fall between 1 and 14. In a lab, anything is possible. So, what is the pH of a 2.0 molar HCl solution? How are you going to calculate that?
Log. Yeah. And I'm gonna throw a negative log in this.
Negative log of
2.0.
2.0. pH is negative log of our H3O plus concentration. 2.0, since this is an acid, 2.0 is our H3O plus concentration. So what is the negative log of 2?
I got a negative
Negative
0.3. Wait.
So what did you get?
Is it,
So what did you get?
Negative 0.3.
Negative 0.3. So that's not between 1 and 14. If you get a concentrated acid, it goes negative. But this concentrated of a thing doesn't really exist in real life. But in lab, that's nothing. On Thursday, we used 6 molar HCl. That 6 molar that you use, locked in a cabinet in the lab, is actually 12 molar HCl. So that is negative 1 point something pH.
Negative 0.77.
Negative log of 12?
What? Yeah, negative what?
Which number did you calculate?
I did 6.
Oh, you did 6. Okay, yeah, that makes sense. I did 12.
Which one of us was right?
We just did different problems. We're both right. I said what you used in lab was a 6. but locked in a cabinet that they used to make the 6 is a 12.
Oh.
Okay.
So we go from a pH 8 to a pH 9. What factor does the H3O plus change by? 10. pH is different by 1, so it changes by a factor of 10. What factor does it change by when you go from a 4 to a 2? 100.
You wouldn't list the negative?
Well, it's a factor.
But it changes.
It's a factor of 100. Then you have to figure out, does it increase by 100 or does it decrease by 100? So if we go from 4 to 2, is it increasing by 100 or decreasing by 100? Think about
It's an increase.
it. Which is more acidic, pH 4 or pH 2? 2. So if it's more acidic, the H3O plus must be higher. So if going from a 4 to a 2, the H3O plus is increasing by a factor of 100. So if you go from 8 to 9, is it increasing or decreasing? It's decreasing by a factor of 10. Here we have some soil. We do a measurement on it, and we get the hydroxide ion concentration is 5 times 10 to the negative 7. What is our pH?
2 times 10 negative.
You doing it in your head?
Oh, pH.
What just happened?
pH. We're given hydroxide ion concentration. It's asking for the pH. How do you do that?
You have to find the acid.
You have to figure out the H3O plus from this, and then you can calculate the pH. So we have this equation, right? We're given that is 5 times 10 to the negative 7. So what is our H3O plus?
2 times 10 to the negative 8.
What is it?
2 times 10 to the negative
2 times 10 to the negative 8. So you took KW and divided by 5 times 10 to the negative 7 to get 2 times 10 to the negative 8. So now, what is the pH? So we have the negative log of 2 times 10 to the negative 8, which is what?
Negative 7.7. 7.7.
Everybody agree?
7.9. So yeah, 7.
Everybody get this?
Yes.
So the pH is 7.7. Is the soil acidic or basic?
Basic.
It's basic. It's 7.7, which is higher than 7. 7 is neutral, so 7.7 is basic.
Got him.
What's wrong? Is that wrong or is he wrong?
Well, chemistry class.
I think that's wrong.
Is this wrong?
I think so.
It's the PowerPoint
What's-
that's wrong. And that's the chemistry class. They're telling us.
1 times 10 to the negative 14 divided by 5 times 10 to the negative 7 is?
No. Can't beat this kid. Oh, yes, it's negative 14.
Exactly.
Negative 8.
I think we should what you're doing is, it's negative exponents, you add 1, divide by small.
Does that equal 2 times 10 to the negative 8? And then the negative log of that is 7.7?
Yeah.
Okay.
Is it the same thing as doing
Whoa,
Two
whoa, whoa.
times 10 to the negative
10 to the negative
Then,
15 divided by 5?
if this number was already on your slide, cross it out. It's 7.7. Doesn't even have the right number, see?
It's 7.7.
It's 7.7.
Who wrote those
Yeah, I
slides?
love this.
Not me. This is McGraw-Hill did. Well, fun McGraw-Hill.
There's a lot of like spelling errors in it. Again, it's kind of irrelevant, but like.
Are there? Are there?
Yeah, I was going back over the last one before I got here.
Because
Because I overslept from work before I got here.
Interesting.
And I had to do the homework. But I was going through it, there's like so many spelling errors. It was just
So,
driving me insane.
because this is wrong, their answer here is going to be wrong also.
Is it?
Right?
Yeah.
Because it's gonna be,
That says it's acidic. So make sure you get the, this is 7.7. This is basic.
what could they have done to make it like that far off?
My guess is, did they take negative log of that? What's the negative log of 5 times 10 negative 7? Yes?
6.3.
Yeah. But they didn't catch that they didn't catch with their own trick question.
Oh, wow.
Here's some more. What's the pH of that? So you got the negative log of that is apparently 3.1.
3.7.
Here's number 2. How am I going to get the pH of that?
Sorry.
How did you get that?
Negative log of 1 times 7 related
It's just it's sodium hydroxide.
to. Oh.
So 0.01 is our hydroxide ion concentration.
Oh.
0.01. So then what is that?
Okay.
That's going to be 10 to the negative 12.
I got 12 fine.
Right. So if this is 10 to the negative 2, exponents have to add to negative 14. So that has to be 10 to the negative 12. Negative log of that is 12. What about this one? Yes, you can.
Would you start with 2 hydrogen ions?
Listen to Darian.
Negative hydrogen ions.
You have 2 hydrogen ions.
We need 3.
Well, listen to the first part of what Darian said.
Listen, Chris. Nobody
So, if we have 1 molar H2SO4, what concentration of hydrogen ions do we have? 2 molar. 1 times 2. So H3O plus equals 2.0 molar. So, what is our pH? pH equals negative 0.3. Same thing we had before.
Right, you do the negative log.
Yeah, the negative log of 2 is negative 0.3. And so, just like with our K values, and I'll point out now, pHs don't have units. So this is another example where you can actually write something with no units and not get expansion. Not only do we have pH, we also have pOH. So it's the same exact equation. pOH is negative log of OH minus. It works exactly the same, but you're using the OH minus to calculate pOH. In pH plus pOH is equal to positive 14. Because if these two here have to be 1, get rid of 1. This is 10 to the negative 7, and that's 10 to the negative 7. What's my pH? What's the negative log of 10 to the negative 7? 7. What's my pOH? 7. 10, negative log of 10 to the 7. So pH is 7, pOH is 7. These two added together equals 14. So the pH plus the pOH is always 14. So if I have a pH of 4, what's my pOH? 10. That's simple. Okay. If you have the pH and the pOH, you can find the other. Ooh, look at that. I don't know what I just did.
Chemistry goes.
Chemistry
Yeah,
class.
it's a- Oh. Yeah, right, that's understanding.
So here are going between pH and negative pOH. We're measuring a soil sample, and we measure the pH is 6.2. Okay? pH is 6.2. What is the H3O plus concentration? This is going in the opposite direction. So basically what we have to do is undo our negative log. And we undo a negative log by taking the pH and going 10 to the negative pH.
Oh.
So what is 10 to the negative 6.2? Correct your syntax. 10 to the negative 6.2.
6.3 times 10 to the negative 7.
6.3 times 10 to the negative 7, and now our molarity magically comes back. So if our H3O plus is 6.2, we can 10 to the negative 6.2, and we get 6.3 times 10 to the negative 7.
6.31.
Say McGraw-Hill, they get the stamp. Stamp of disapproval.
Definitely kind of.
So these are hydrangeas. Hydrangea color is actually partially dependent on soil pH. So if I tell you that hydrangeas are blue in acidic soil and pink in basic soil, if you grow a hydrangea in this soil, what colors are going to be? If blue is acidic, pink is basic. It's going to be blue. pH is 6.2, which is acidic, so you'll get blue. So now we know how to calculate pH, pOH, OH minus, and H3O plus. So this creates a perfect storm for homework problems and quiz problems. Because if you know one, you can calculate all the other three. If you got pH, you can get pOH, is 14 minus pH, pOH. Take 10 to the negative pH, you get H3O plus. And now then you would have options of how you want to get that. You either go from there to there, or there to there. So I guarantee you, probably multiple times the rest of the semester, you'll see a table. And off the top are going to be these four things, and for each line, you'll be given one of the four, and you have to calculate the other three. So you're going to need to be able to go to each of them, from one corner to all the other three. One piece of advice, if you start with pH, the easiest thing to calculate is pOH. So you can get from pH to pOH by going like that. But the more you do it, you'll very quickly realize pH to pOH is the simplest math. There's no exponents involved, there's no logs involved, there's nothing. So if you got one of these two, go straight to the other one, rather than going the roundabout way. So here's a problem. It says, if a lake goes below 4.5 pH, it's dead. We find the lake, we measure the OH concentration as this. Is the lake dead? No. How did you get to know that quickly?
Because it's, you know, 1.0 times pH.
Would be dead,
Wait, no.
How are you getting to that?
Yeah, it's gonna be a 9 pOH, which is gonna be a
Right.
5.
OH minus concentration is 10 to the negative 9, so the pOH is equal 9. If the pOH is equal to 9, what is my pH? 5. And so is 5 larger or smaller than 4.5?
Oh, I was thinking just acidic.
It's larger. And so is 5 more or less acidic than 4.5? It's less acidic. And so this lake is not dead. I wouldn't want to swim in it, but it's not dead.
What would happen if you stopped it?
Oh, it might burn your eyes. Exfoliate your skin.
Positive ways to look at it.
There are a number of ways that we can measure pH in lab. And we're going to do all of them, I believe, once we get to the pH lab. If you have a fancy dancy pH meter, you just stick it in and it tells you. There's also strips that you put it in and it changes color based on the pH. And you compare it to the container. Whatever color you get, it tells you what pH that is. You'll do this, I believe, and you'll do this. And then, anybody ever do water testing when they were in school? If you were in the pH group, you probably had a kit that looks similar to that, and you added different dyes to it and saw what color came up. You figured out what pH it was. We can also use phenolphthalein. You used phenolphthalein in lab a couple weeks ago. How did you use it?
You mixed it with something else and do something into a solution and see what comes out.
So safe.
Yes.
I'm sure we didn't mix it.
That's a good answer on the test.
Does anybody remember with more detail
I'm good at writing.
what we did with phenolphthalein in lab? Maybe it had to do with acids and bases.
Oh,
It
did
was
we
the
stir it?
swirl, yes. It was the one you swirled. So what were you swirling? What you did is you took acid, you added the phenolphthalein to your acid. You added the phenolphthalein to your acid. And this says, in acid, phenolphthalein is colorless. So you put it in there, you had it in your Erlenmeyer, in your acid, and it was clear. And then, drop by drop, you added base. So if you remember, when you added a drop of base, you got a little puff of pink. And then when you swirled it, it went away. Because when you added the base, right where that drop hit, all of a sudden it became basic. But then once you swirled it, you mixed it with all of the acid, and it became acidic again. So you added it drop by drop by drop, until all of a sudden you neutralized all of the acid. And now when you added that next drop, all of a sudden we had more OH minus than H3O plus, it was now basic, and it turned pink. So this is an example of a pH dye. There are a lot of different pH dyes out there. And you can determine which one you want to use. I guess that's the next slide. So this is more or less what you did. Okay. Started with clear. You added a little bit by little bit, and it went to light pink. And as you added more, you went to dark. So these are examples of pH dyes. So you use pH dyes when you're doing titrations. We're not doing titrations per se in our lab. An actual titration is a quantitative measurement where you take a base and you add it drop by drop to an acid of unknown concentration. So if you know how much base you added, you can calculate how much acid had to have been there, but that's not something we're doing. And so what you do is you pick a dye that changes color at a pH very close to where you think you are. And so if you're starting up here and you pick methyl violet, you're going to be adding a whole lot of acid, where if you're actually adding base, you're going to go that way. You're not going to see anything. So you pick a color that's near where you're starting, so you just add it until you see your color change. And then when you see the color change, you know that's the pH that you're at. So this is a titration. So if you have a titration, it's just adding an acid to a base or a base to an acid. For example, HCl plus NaOH, when you do that, it's a double displacement reaction, but it's an acid-base neutralization. You're going to get sodium chloride and water. If you're doing a titration, looks just like our dilution problem. C1V1 equals C2V2. C is concentration, it's going to be molarity again. V is volume, 1 is acid, 2 is base. If you want to switch them around, that's okay. But one side is acid, one side is base. So if you're going to add some acid to a base, and they're going to exactly neutralize each other, the concentration times the volume of the acid is going to be equal to the concentration times the volume of your base. So if you have an acid, you know how much volume you have, but you don't know what concentration it is. You can drop by drop add a base that you know the concentration of, and then when you hit that point where the color changes, you know the two are equal to each other. You look up how much base you've added. So now you know both of these and that, so you can calculate how concentrated your acid was to begin with. So if we have this, it's asking us what is the hydroxide ion concentration if we mix this with this. Okay? Actually, let's take a, this is a tricky question. Not tricky, but difficult. So let's do that after the break. So let's come back at 20 till on that clock. That at least.
Did we then necessarily, because I had that contact over the lady at the DRC downtown, I get something that.
Yeah. So that, we have the equilibrium. So you can, the first one, you're gonna add your, if you add ammonia to that equilibrium, which way is it gonna shift? It's gonna shift to the left. So that's the first half of that. Gonna move to the left. So after it shifts, is your N2 going to go up, down, or not change? You go up. Correct. Good, you're adding. What it does is if you double the volume of your container, they're all gases. In this section, they're all gases. So if you double the volume of the container, you're going to have all the concentrations. So if you look at the KQ equation, you're going to have the top, you're going to have the bottom. So mathematically, it has no effect. And so it has no nothing will change. Right? Add a catalyst. The catalyst makes. Okay. Yeah, we didn't go over that. But just so you know, what a catalyst does is it will make it get to equilibrium faster, but it won't change the equilibrium.
Absolutely.
So it would have nothing will change. So the equilibrium is not going to shift, but if you add some to both sides, if you add H2, the H2 is going to go up. So if you add NH3, NH3 is going to go up. N2 is going to have to go up also, so that you don't shift the equilibrium.
But it wouldn't shift, it wouldn't have
No. It's just, it's going to find its application. That's true.
That's the makeup.
Oh, I'll take it, yeah. Did you get a hand cramp from writing all this?
Yeah, but I kind of split it up, so it wasn't too bad.
There's a lot there. Because that's normally on an online class.
Yeah, well, and she always offers either a morning or an online, so. And it's always the same lady, so I'm just glad I'm leaving her program, so. And even at Dr. When students and all of them are kind of in my same boat, and so none of them are very happy with her. So, yeah.
We'll get it figured out. Class switch from Coke to energy drinks.
Good of that time of the year.
Yes. It doesn't help when it gets dark at 6 o'clock.
I know, it's.
Yeah, but I think right now, I never go to sleep, I'd be up all the rest of the night.
Why do you crash usually?
Oh, yeah. Like half an hour before I gotta go to work, I'll be like, great.
I wish caffeine still had that effect.
And it sure does have, because you get so used to caffeine. I remember years ago, like I would drink these little energy drinks that were like, they were called Rippets, are the ones from the Dollar Tree. And I got to a point where I could drink 7 of them just to like be like awake. You know what I mean? Yeah.
That's not very healthy.
Because you just build up a
How did you
resistance.
not that?
Well, I mean, I drink a lot of water too. So
I'm surprised you didn't have like a heart attack or something.
Yeah, you're
Yeah.
gonna eat your stomach.
I know, right?
Or diabetes.
Yeah, that's because I kept getting my shifts changed so many times. I just, then trouble sleeping. Right from all the caffeine too.
Nah.
Yeah, I can do that.
So you can thank me, I decided to skip this one. This one's more complicated than, I looked at the homework. I'm not sure you have to do any titration, so might as well do an easier example. So here's an easier example of a titration. So it says, it's asking us how much of a stock solution of potassium hydroxide, which has a pH of 0.1, is needed to fully neutralize 13.4 liters of 0.2 molar H2SO4. So our equation was C1V1 equals C2V2. We're going to say the 1s are our acid, 2s are our base. So what is C1? What is the concentration of the hydrogens in our acid?
0.2. Oh wait. That's your time.
Nope.
Oh wait, no.
0.4. 0.2 molar H2SO4, and you get 2 H's out of it. So it's 0.4 molar. So C1 is 0.4. What is V1? Times 13.4 equals, what is C2? We get it from 0.1, but we need molarity of hydroxide ion. We have pH.
You do the opposite.
So you're the opposite.
Something like backwards,
Like,
basically. maybe
yeah,
like
that's
one,
what-
C1.
10 to the negative 110.
Something like that.
If pH is 0.1, we're dealing with OH.
Well,
So I would immediately go to POH. What's my POH?
13.9.
That POH is 13.9. 13.9 plus 1 is 14. So now I need to get OH minus concentration of POH 13.9. So it's 10 to the negative 13.9. And so that, I'm just going to take that, stick it in for my C2, rather than actually figuring out what that is. Times V2. V2 is our unknown. So V2 equals 0.4 times 13.4 divided by the negative 13.9, which is what?
Two, 4.3 times 10 to the 14.
Depends on when you do sick days.
Yeah, depends what I'm.
I would just do them at the end.
It's a 4.25.
Well, there's only one sick day. So 4. 4 times 10 to the what?
Yeah, 14.
10 to the 14th, and what is my unit? The volume.
That's
To the
easy.
negative.
Liters. This was liters, so my V1 was liters, so my V2 is going to be liters. 4 times 10 to the 14th is liters. 4 to the times 10 to the 9th is 4 billion. And so 4 times 10 to the 12th is 4 trillion. And so you're at 400 trillion liters.
So you're not.
We can do it!
Now think about it.
I believe.
Does this, I mean, that's a lot. That's something that should make you stop and think, oh crap, I did something wrong.
Yeah.
Okay? But look at the problem. We have acid, right? We're going to neutralize it with KOH, and our KOH has a pH of 0.1.
There's none.
If I told you you had a solution that was pH 0.1,
It's very acidic.
it's acidic.
You're not gonna neutralize an acid with an acid.
But we calculated a concentration the OH minus concentrations tend to the negative 13.9. So if you have a KOH solution of 10 to the negative 13.9 molar, that will be your pH. And so the reason it takes so much is because, yes, you are neutralizing an acid with an acid.
Isn't that basically just putting so much water in it that water reaches equilibrium?
Basically. Basically, yes.
Fighting fire with fire.
Yeah. Which is why it's huge. And so it does make sense that it's huge. So you trust your method. Okay. So now we've talked about acids and bases, conjugate acids, conjugate bases. We can go on to how we can use these in the lab. And we can use them to make buffers. A buffer is a combination of a weak acid and its conjugate base, or a weak base with its conjugate acid, in such a way that there's roughly the same amount of both of them. In our blood, we have the bicarbonate buffer system. So this is carbonic acid. This is bicarbonate. Which one is the acid? Which one is the conjugate base?
So carbonic acid is the acid.
Carbonic acid is going to be the acid. And so carbonate is the conjugate base. There's one hydrogen apart. If you want to make a buffer, you need one of these pairs. And if you have one of these pairs, there's going to be one hydrogen apart. So if you are asked, which of these pairs of things can be used to make a buffer, you pick the one where they're one hydrogen apart.
What if none of them are hydrogen?
Then you can't make a buffer out of it. So, if you have roughly equal amounts of these, we're going to start here in the middle. We have equal amounts of our bicarbonate and our carbonic acid. If we take that buffer and we add acid to it, we're adding an acid, but we have a base. We have a base in there for it to react with. So the acid that we add is going to react with our conjugate base. And so the hydrogen from here is going to go onto here. When you add a hydrogen to that, what do you get?
H2, excuse
You get that, right. And so what happens is it takes your acid and converts it, it reacts with a base to make this. But this is a weak acid. This presumably came from something like HCl, which is a strong acid. So more or less what it did is it took a strong acid and converted it into a weak acid. And so adding that acid is not going to have a very large effect on the pH. What a buffer does is it prevents large pH changes. If we take this and we add something like sodium hydroxide, we're adding OH minuses, but we have acid in our buffer. So the OH that we add is going to react with our acid. And if you react that with OH minus, what are you going to get? You're going to get that. So you took your NaOH, your strong base, and converted it into a weak base. And so you don't change your pH very much.
And why is this good for like your blood, for your body?
Because enzymes in our body, everything in our body is run by enzymes. And enzymes work best at a specific pH. And so, when you drink that Monster, I'm guessing that Monster is pretty acidic.
You're probably right.
You don't want that changing the pH of your blood, because all of a sudden your enzymes are going to stop working, and you'll just fall over. And so you need a buffer in your blood to keep your pH at roughly 7.4. Physiological pH is right around 7.4. So, can you use that to make a buffer? No. They're not even the same, close to being the same thing. Also, not only are they not the same thing, that's a strong acid, that's a strong base. They have to start with a weak acid or a weak base and its conjugate acid or base. Can you use these?
Yeah.
Why?
Because you add a hydrogen.
There's one hydrogen,
Or you take away hydrogen.
right, there's one hydrogen difference between them. Where does the sodium come from?
Presumably
So
sodium.
you want to make a buffer, okay? This is acetic acid, okay? You have to add your weak acid and the conjugate base. What is the conjugate base of this? CH3CO2 minus. There's going to be a negative charge on that. So you have to then, to make a buffer, you have to add CH3CO2 minus. But you can't go to the shelf and get a bottle of CH3CO2 minus. Because ions don't just exist. If you put that into water, what are you going to get? Na plus and CH3CO2 minus. So this is your source of your CH3CO2 minus. Once you put it in the water, the sodium just floats away and minds its own business. But when it's in a bottle on the shelf, you have to have this whole ionic compound. So you're going to mix these two things in your solution. Can you use that to make a buffer? Why?
There's only one hydrogen, and then there's no hydrogen.
So it's one hydrogen apart, right? It's the same thing we did here. We replaced the hydrogen with a metal.
But there's hydrogen on both sides of the equation. There's no hydrogen.
Wait,
I'm talking about the one above, there's hydrogen on both sides.
these hydrogens those are not acidic. They're connected to the carbon. Only this one hydrogen actually does anything.
Oh,
I would say you can, yeah. Potassium bromide is an ionic compound, it's gonna break apart. So it calls you to get HBr and.
What kind of an acid is HBr? It's a strong acid. You can't use strong acids in a buffer. They have to be weak acids in their conjugate base, or a weak base in their conjugate acid. So even though they're one hydrogen apart, that's a strong acid, so you can't use to make a buffer. Unfortunately, our pH does change. If he drinks enough Monsters, his pH is going to change. Okay? And this can cause big problems. If your pH drops, it's called acidosis. And lots of stuff goes wrong. So like we said, enzymes depend on pH. And enzymes run everything in our body. Anything in our body that does anything is an enzyme. And if the pH changes even a little bit, your enzymes aren't going to work nearly as well. So we have mental problems, muscle problems, diarrhea, heart problems, breathing problems. You need Pepto and a whole bunch of other stuff. Okay? A lot of stuff is going to go bad. This is acidosis. Okay? It's the phenomenon is called acidosis. If you want to describe a patient that has acidosis, you would say that patient is acidotic. That's just terminology. So, this is bicarbonate buffer system. So, normally, that is our bicarbonate. So that's our carbonic acid. if we go this way, we get CO2. So if we, in the lab, we remember when you blew into the barium hydroxide, barium hydroxide, you said you were adding CO2, which made it acidic. So if you add CO2 to water, you get carbonic acid, which your body can then break down into bicarbonate and H+. Okay? So, if you are here, say you're acid, you have acidosis. You're supposed to be here. Which way have you shifted on that equilibrium? You have too much acid. What down here is right. If you have too much acid, you have too much H+. So you're supposed to be here, you shifted over here. There are two types of acidosis, and it depends on what's causing it. If you're acidotic, your pH is going to be less than 7.4. First type is respiratory acidosis. What in this equilibrium has anything to do with respiration? CO2. So, if you have too much CO2 in your blood, say you have this equilibrium, and you add CO2, which way are things going to shift? Left or right? They're going to shift to the right. If you add this, it's going to shift to the right. So if you add CO2, you make more of that, which makes more of this. Adding CO2 makes more acid.
So that's what happens when you hyperventilate, right?
So let's think about it. If you're hyperventilating, are you breathing a lot or not enough?
A lot.
You're breathing a lot. What purpose does breathing have to do with CO2? It gets rid of CO2. So if you're breathing a lot, you're getting rid of CO2, and this whole thing is going to shift left. You're going to lose your acid. Yes?
So when you exercise, you become less acidic?
No. You're breathing a lot for two purposes. One, you need more oxygen.
Yeah.
When you exercise, you make lactic acid, which is acid, and you have to get rid of that acid. So by breathing a lot, you're breathing out CO2, trying to get rid of that acid that you're making. So it serves both purposes. And so, in what situation could you get respiratory acidosis? What would happen to make you acidic that has to do with your breathing?
Not breathing.
Not breathing enough.
Not exhaling.
Yeah, well, you can't exhale without inhale, so you're not breathing enough. In what situation would you not breathe enough? I mean,
If you're underwater.
Sedation.
Theoretically.
most likely, if you're underwater, you're gonna die of lack of oxygen before you die of this. But if you're under sedation, you start breathing really shallow.
But breathe into a really long tube.
What?
There's a story about a dude underwater,
Yeah.
he had too long of a tube, he
Yes.
started breathing his own
He
carbon
started
dioxide.
breathing his own, exhaling CO2, and it wasn't coming out the tube, so he was just breathing his own CO2 back in and out and in and out. And so if you're someone that's really weak, I mean, they were just in a bad accident and they can barely breathe on their own, over a long period of time, this is slowly gonna shift over. And over a long period of time, they're gonna become acidotic, because the CO2 that they're making is going to slowly build up. The other type is metabolic. Your kidneys make bicarbonate. Your kidneys make base. So what would happen to your kidneys that would make you acidotic? Kidney failure. If you have kidney failure, your kidneys are going to stop making base. If your kidneys stop making base, you're going to become acidic.
What about kidney stones? Should that have any impact?
Probably not. Kidney stones would block the flushing. I suppose if the kidney stone was in a place that would block the secretion where your kidneys were making this, but it couldn't secrete it in the bloodstream, it may cause it. So let's think about how we can fix this. If you're acidotic, what can you do to fix it? Hyperventilate. If you're acidotic, if you start breathing a lot, you're going to get rid of the CO2, and all of a sudden your acid is going to come this way. You're going to basically be exhaling all of that extra acid. Now, if you're acidic because you can't breathe, then hyperventilating isn't really an option. But if you're acidic because you have kidney problems, then you can temporarily fix that problem by breathing until you black out. And then you
Then you have all of them.
I guess metabolic acidosis, say if you're exercising. Say you're exercising, but you're not exhaling enough. Then you're making too much acid. Metabolic acidosis is either because your kidneys aren't making enough base, or for one reason or another, you're making too much acid.
You don't breathe. So it's like they breathe out when you're.
The opposite of acidosis is alkalosis. So the patient would be alkalytic. Again, there's respiratory and metabolic alkalosis.
So alkalytic would be when
If
Don't
you're
breathe.
hyperventilating
Yeah.
for just because you're stressed or something like that. If all of a sudden you start hyperventilating, you could become alkalytic. You ever seen somebody starts hyperventilating and they start breathing into a bag? What's that going to do?
you're breathing up your
You're breathing in your CO2. So you're hyperventilating, but you're then breathing that CO2 back in. So you're not losing that CO2. It's like breathing in the big long tube. So that's going to help.
That's how the ninja dies.
What would cause metabolic
What did you?
alkalosis?
Your kidneys not producing enough.
Your kidneys make too much. Your kidneys make base. So your kidneys make too much base, or something in your body is not. What normally makes acid is not making as much as it normally would. And so, in relation to how much your kidneys normally make, all of a sudden the kidneys are overpowering how much acid you're making. So if you're alkalytic, how can you solve that problem temporarily?
Don't breathe.
Hold your breath. If you hold your breath, CO2 is going to build up in your body. If you're feeling bad and you're alkalytic or acidotic, you can't really change what your kidney is doing. But you can mentally change how you're breathing. So short term, you can change these situations by breathing. That's not necessarily a good long-term situation. You don't want to have to breathe really fast for the next 30 years. You probably want to figure out what's going on with your kidneys. There are a couple other buffers in our body, but bicarbonate is by far the biggest one. One of the other ones is a phosphate buffer, which is phosphoric acid with its conjugate base, H2PO4 minus. And then hemoglobin. What is hemoglobin? Hemoglobin is the protein in your blood that holds oxygen. But it itself can act as a buffer. So these things kind of help, but the bicarbonate is by far the biggest thing. Yeah.
I heard a story one time about a guy who didn't build up lactic acid in his muscles, like he didn't produce lactic acid. I don't know, would that be like, relevant?
That was on Stanley's Superhumans, right?
Yeah.
The dude that could run forever.
Yeah, under no circumstances did he build up any, like,
What I'm just completely making stuff up. Well, not making it up. I'm making a hypothesis. Okay. What I would guess is your cells can make energy two different ways, with and without oxygen. If they make energy with oxygen, you don't make lactic acid. Okay. But when you exercise a lot, the oxygen can't get in your muscles fast enough, and it's a switch to the other method, which makes lactic acid. Okay. But there are enzymes that has to occur, that you make that process work. If you had a genetic deficiency or a genetic disease where that enzyme didn't work, you could only make energy using oxygen. So in that situation, you would never make the lactic acid.
Well, this dude, he made it for a certain amount, and then his body would start clearing it until he came back down to a normal level, and it would never
Really?
rise. So his body would build it up a little and then clear it out faster than it could be made.
So my guess is, there are also enzymes whose role is to go back, take this, make it into that, and then your lungs go from there to that. So if he was able to, if he had a lot of the enzyme that took the acid and converted it into carbonic acid so that he could exhale it, I mean, so if a normal person like myself was running, I can exhale all I want, but if my enzyme can't convert my lactic acid into carbonic acid fast enough, I can't exhale my CO2. So that would be my guess.
Was it?
He ran like 50 marathons.
So that is it. That is the end.
Is it fun?
Take your fun.
You don't want to take
Your
the
final.
final. You don't want to take the final. But we can talk about the final now. So,
Can we not take the quiz?
you gotta take the quiz. Guys, gotta take the quiz. So this week has normal homework. Okay? But this is homework 13. Homework 14 and 15 is another cumulative one. Okay? It is already available on campus. You can start it whenever you want. The next 2 weeks in here are going to be one ginormous quiz bowl. Okay? 6-hour-long quiz bowl. There will be quizzes at the end, so yes, you have to show up. Okay? Because next week's class will have the quiz on today's stuff, and then there will be a quiz at the end that we can talk about when we get closer. Okay, so you do need to show up, but what we're going to do is go over that final homework 14, 15 cumulative homework, question by question. Not just multiple choice ones, not the written ones. So I put it on Canvas already, so if you want to print it out and bring it to class for when we go through it, you can.
So we're going to start going through it next Tuesday?
We're going to start from number 1 next Tuesday. And we should be able to get through all of them in 2 weeks. That is your study guide. Okay? Everything that's on the final is in that cumulative homework. That doesn't mean everything that's in the homework is on the final. The homework is much bigger than the final is. But if it's on the final, it is in that homework.
Like the same question?
No, not the same question.
Same.
Wishful thinking.
Same types of ideas. So there are a couple ways you can go about this. If you want to figure out an idea of how you would do on the final, my suggestion would be, before we start going over those questions in class, take a couple hours, sit down, and do that cumulative homework without looking anything up that's not on your cheat sheet. Act like that is your final. And then keep that to the side, and then do what you need to do. So bring it to class, and then we'll go over the right answers in class. You can figure out how you would have done if that was the final. Okay? If you come to class and we start going over things before you do that, you kind of compromise that practice exam. Because now all of a sudden you know the answer. I told you the answer. And then you don't know whether you would have gotten it right or wrong. Okay? So that is your study guide. You do not, your goal is to come into that final exam being confident on every single question on that cumulative homework. If there's one that you don't know, ask me, ask a classmate, wait until we do it in class. If you still don't understand it, ask a question, do something. If you come in to take that final exam and you're confident on everything in that homework, you will do fine. Yes.
When is the final?
December 8th, 5:45. It's Tuesday, but it's 5:45, not 6. I don't set the final exam time.
That's PM.
Yes.
Oh, God.
It is scheduled for 2 hours. I would not make a dinner date